Hi guys! Welcome to Science Moment, a place to ask the big questions, to seek the hidden truths, and to marvel at the sheer scale of the universe we call home. Among the billions of stars in the night sky, there is one planet that always makes people pause a little longer. Not because it is the brightest, nor because it is the closest, because it's like us, yet so terrifyingly different from us. That is Mars, the red planet, the planet of war in ancient mythology, and the planet of unanswered questions in modern science. A world that once had water, rivers, and conditions for life to exist. But today only dust, ice, and a silence that has lasted for billions of years remain. What happened? Why did two planets born from the same material, Earth and Mars, follow two completely different paths? And more importantly, could Mars' story be subtly foreshadowing something about our own future? In this video, we'll follow the journey of Mars from a warm, wet planet to a cold, desolate wasteland to understand not only Mars, but also the fragility of life in the universe. Mars, from planet of life to a desert world. Introduction. Why does Mars always fascinate humanity? Since humans first gazed at the night sky, Mars has always been one of the most intriguing celestial bodies. Not as brightly shining as Venus, nor as distant as Saturn. Mars appears with a distinctive reddish glow, different, mysterious, and somewhat unsettling. It is this color that has led to the planet being associated with war, bloodshed, and conflict in many ancient civilizations. In Roman culture, Mars was named after Mars, the god of war. The Greeks called it Ars, also the god of violence and chaos. In ancient China, Mars was called Huixing, associated with bad omens, turmoil, and great upheaval. Despite differences in language and belief systems, these civilizations inadvertently agreed on one point: Mars is not an ordinary planet. However, behind that mythical symbolism lies a deeper scientific truth. Mars is the planet with more similarities to Earth than any other planet in the solar system. It has a day-night cycle nearly identical to Earth's, an axial tilt that creates seasons, and once had volcanoes, rivers, and possibly oceans. It is this familiarity and difference that has made Mars a prime subject of study for modern science. When telescopes developed in the 17th century, Mars was no longer just a vague red dot. Giovanni Schiaparelli observed lines on its surface which he called canali. Although the word in Italian simply means groove, it was mistranslated as canals, artificial canals. From then on, human imagination exploded. People began talking about Martian civilizations, about intelligent beings trying to bring water to save their arid planet. Although these theories were quickly refuted as science advanced, they reveal one important thing: Mars has always been considered a candidate for extraterrestrial life. This is no coincidence. Scientists have realized that if life ever existed anywhere else in the solar system, Mars has the highest probability. From the late 20th century to the present day, space missions have continuously focused on the red planet. Orbiters, landers, and rovers have been sent one after another to answer fundamental yet challenging questions. Was Mars ever like Earth? If so, what caused these two brother planets to follow two completely different paths? These questions are not merely academic. They directly relate to the fate of Earth. If we understand why Mars lost its water, atmosphere, and ability to sustain life, we will better understand what factors are keeping Earth alive and what could cause its decline. In other words, studying Mars is not just about looking into space. It's a way for humanity to reflect on our own planet, to understand that life is not a given, but the fragile result of a delicate balance of conditions. 2. Formation and basic characteristics of Mars. Mars formed approximately 4.5 to 4.6 billion years ago, almost at the same time as Earth and other planets in the solar system. It emerged from the same giant cloud of dust and gas, the remnants of an ancient supernova explosion. This means that, in terms of their initial material composition, Mars and Earth are siblings. However, from the very beginning, the difference in size laid the foundation for the two planets' different destinies. Mars is about half the diameter of Earth and only about 10% the mass. This smallness means Mars' gravitational pull is significantly weaker, leading to many long-term consequences. Internally, Mars consists of three main layers: the core, the mantle, and the crust. Its core contains iron, nickel, and a large amount of sulfur. The presence of sulfur lowers the core's melting point, which directly affects its ability to generate a magnetic field. Surrounding the core is a silicate mantle, similar to Earth's, and the outermost layer is the iron oxide-rich crust, the cause of the planet's characteristic red color. The red color of Mars is neither blood nor lava, but the result of iron oxidation similar to rust on Earth. This suggests that the Martian surface was once exposed to oxygen and water, at least to some extent. The surface of Mars boasts many impressive geological features. Most notable is Olympus Mons, the largest volcano in the solar system, nearly 3 times the height of Mount Everest. The existence of these colossal volcanoes reflects an important fact. Mars lacks the plate tectonics found on Earth. On Earth, moving tectonic plates make it difficult for volcanoes to grow too large. On Mars, the planet's crust is almost stationary, allowing lava to accumulate in a single point for hundreds of millions of years. Furthermore, Mars possesses some of the deepest and longest canyons in the solar system, most notably Valles Marineris, over 4,000 kilometers long and many times deeper than the Grand Canyon. These structures indicate that the red planet experienced intense geological activity in its early stages. However, over time, Mars gradually cooled down. Volcanic activity decreased sharply, the core cooled, and endogenous processes slowed down. This was the first step in a chain of events leading to the planet's decline. 3. Ancient Mars, the warm and wet planet. In stark contrast to its present-day arid image, ancient Mars may have once been a warm and humid world. This is no longer a science fiction hypothesis, but a conclusion built upon a wealth of clear geological evidence. Orbital spacecraft and autonomous robots have discovered traces of ancient rivers, eroded valleys, deltas, and dried-up lakebeds. These structures have distinctive shapes that could only have formed due to the flow of water over extended periods. It's not just fleeting water, but a relatively stable hydrological system. Many large impact craters on Mars once contained deep lakes. Some areas, such as Jezero Crater, where the Perseverance rover is operating, show traces of deltas, similar to river deltas on Earth. This suggests that water carried sediments, deposited them, and restructured the planet's surface over millions of years. For water to exist in liquid form, ancient Mars would have had a much thicker atmosphere than it does today. Atmospheric pressure could then have been high enough to prevent water from evaporating immediately. At the same time, the greenhouse effect from CO and possibly methane helped retain heat, keeping average temperatures above freezing. In such an environment, Mars may have possessed the basic conditions for life: liquid water, a source of chemical energy, and essential elements. Although there is no direct evidence of ancient life, many scientists believe that Mars at this stage was at least habitable. However, this warm and wet period did not last forever. A series of profound changes within the planet gradually pushed Mars away from an Earth-like path, initiating an irreversible process of decline. 4. Magnetic field, a determining factor in Mars' fate. If one had to choose a single factor determining the long-term fate of a rocky planet, it wouldn't be water, nor its atmosphere, but its magnetic field. The magnetic field is an invisible shield protecting the planet from the constant onslaught of solar wind, the stream of high-energy particles blown out from its central star. On Earth, the magnetic field is created by the dynamo effect in the liquid outer core, where molten iron moves and rotates with the planet's rotation. This magnetic field not only powers compasses, but more importantly, it protects the atmosphere from being blown away, while also helping to retain heat and water on the surface for billions of years. Mars, in its distant past, also had a strong magnetic field. This is no longer speculation, but confirmed by measurements from the Mars Global Surveyor spacecraft. Many areas of Mars' ancient rocky crust show signs of strong magnetization, indicating that when they formed, the planet still had a stable, active global magnetic field. Mars' ancient magnetic field likely existed for the first few 100 million years, precisely the period when liquid water became widespread on the surface. This was a crucial period. While the magnetic field persisted, Mars was able to maintain an atmosphere thick enough to sustain the pressure and temperature suitable for water. However, the difference in size soon revealed its consequences. Mars is smaller than Earth, so it cooled down faster. As the planet cooled, its metallic core gradually lost heat. Convection weakened, and the dynamo effect began to flicker and then cease. Another factor is the chemical composition of the core. The Martian core contains a high amount of sulfur, making it prone to stratification. The heavier layers sink, the lighter layers rise, hindering convection, a vital element for maintaining the magnetic field. When convection ceases, the magnetic field disappears as well. It's noteworthy that this disappearance didn't happen suddenly, but rather as a prolonged process. During that time, the magnetic field weakened, like a shield with increasingly large holes. The solar wind began to penetrate deeper, interacting directly with the upper layers of the atmosphere. When the global magnetic field collapsed, Mars lost its most crucial protective layer. From this point on, the fate of the red planet was practically sealed. Consequences of magnetic field loss. When Mars loses its magnetic field, it enters a phase of irreversible decline. The solar wind, which was previously deflected by the magnetic field, now crashes directly into the atmosphere. High-energy particles collide with gas molecules, transferring enough energy to cause them to escape the planet's weak gravitational pull. This process is called atmospheric erosion, and it occurs slowly but continuously over billions of years. It's not an instantaneous catastrophe, but rather an invisible bleeding. The Martian atmosphere thins, pressure decreases, and the greenhouse effect weakens. When atmospheric pressure drops below a certain threshold, liquid water is no longer stable on the surface. The water begins to evaporate rapidly, even at low temperatures. This water vapor is then further dispersed by the solar wind and blown into space. Other water froze, particularly in polar regions and beneath the surface. Over time, Mars lost much of its original water, possibly equivalent to a shallow ocean that covered the entire globe. Along with water, heat is no longer retained. The global average temperature has plummeted. Warm climate cycles have disappeared, giving way to a cold, dry, and harsh planet. Chemical reactions necessary for life have slowed down or stopped altogether. The important point is, there wasn't a single death of Mars moment. Instead, it was a process of decline spanning hundreds of millions of years. If microbial life ever existed, it likely was gradually pushed into increasingly harsh environments until it could no longer survive on the surface. Mars, once a world teeming with rivers and lakes, has become a frozen desert. The valleys that once flowed with water are now only fossilized remains like the skeletons of a dead planet. 6. Mars today, a harsh world today. Mars is a harsh planet by every biological standard of Earth. Its atmosphere is extremely thin, with over 95% carbon dioxide. Atmospheric pressure is only about 1% of that of Earth, equivalent to conditions at an altitude of over 30 kilometers above ours. The average global temperature on Mars is around -60 degrees Celsius. At night, temperatures can drop below -100 degrees. This large temperature difference between day and night causes the surface to constantly expand and contract, contributing to the formation of fine dust that blankets the planet. One of the most characteristic phenomena of modern Mars is the global dust storm. These storms can cover the entire planet for weeks or even months, obscuring sunlight and severely impacting robotic missions. Regarding water, Mars today no longer has stable liquid water on its surface. However, water hasn't completely disappeared. The planet's poles contain large amounts of water ice, interspersed with co-ice. Below the surface, radars have detected widespread subsurface ice, particularly at mid-latitudes. Some studies also suggest the possibility of temporary liquid saltwater existence beneath the surface, where higher pressure and salt lower the freezing point. While this environment is extremely harsh, it still offers a glimmer of hope for microbial life forms. Mars today resembles a giant natural laboratory where we can observe the ultimate results of losing its magnetic field, atmosphere, and water. It is a grim reflection of a scenario that Earth must avoid at all costs. 7. Potential signs of life. The biggest question modern science is asking about Mars is no longer, what does this planet look like, but whether it ever or still does harbor life. Even though Mars' current surface is harsh and nearly uninhabitable, evidence gathered over the past decades suggests the story may be far more complex. One of the most striking findings is the presence of methane in the Martian atmosphere. Methane is an unstable molecule in a radiation-rich environment like Mars. So if it exists, it must be constantly replenished. Even more noteworthy, the recorded methane levels are not stable but vary seasonally, increasing in summer and decreasing in winter in some areas. On Earth, methane is often associated with biological activity, particularly anaerobic microorganisms. However, science is cautious about this comparison. On Mars, methane can also be produced by geological processes, such as the reaction between water and iron-rich minerals in the mantle, a mechanism known as serpentinization. Besides methane, autonomous robots like Curiosity have discovered complex organic molecules in sedimentary rocks over 3 billion years old. These molecules are fundamental components of life chemistry, even though they are not direct evidence of life themselves. The key here is the context. The organic molecules were found in an environment that once contained liquid water, chemical energy, and relatively stable conditions over a long period. This is the golden triangle for life as we understand it. However, science cannot yet definitively confirm the biological origin of any of these discoveries. All current data lies in the gray area between biology and geology. This leads to 3 main scenarios for life on Mars. First, Mars has never had life. While water may have existed, the conditions may never have been stable or long-lasting enough for life to develop. Secondly, Mars once had life, possibly simple microorganisms, But these became extinct when the planet lost its atmosphere and surface water. Third, life still exists, but it is hidden deep beneath the surface, where there is ice, temporarily liquid saltwater, and it is shielded from radiation. In these three scenarios, modern science has not ruled out any possibility. And it is this very uncertainty that has driven increasingly sophisticated missions, seeking clear biological evidence, not just molecules, but structures, isotopes, and chemical patterns that cannot be explained by geology alone. 8. Mysteries and misunderstandings about Mars alongside serious science. Mars is also fertile ground for imagination and controversial theories. For decades, a multitude of images from probes have been interpreted by the public in ways far beyond their original scientific significance. A key psychological phenomenon behind this is pareidolia, the human brain's natural tendency to recognize familiar shapes from random patterns. On Earth, we see faces in clouds, animals in rock formations. On Mars, pareidolia has created faces, pyramid shapes, stone gates, spoons, and even forests. The most famous example is the face of Cydonia, first photographed in the 1970s. Under low light and resolution, a hill resembles a human face. However, when photographed again with more modern equipment, the structure becomes clear as simply a natural rock formation with random shadows. Geological science has explained much of these controversial images with familiar processes: wind erosion, thermal fracturing, volcanic sedimentation, and meteorite impacts. There's no need for ancient civilizations or extraterrestrial architecture to explain these phenomena. The role of the media is also noteworthy. Sensational headlines often spread faster than careful scientific analysis. This not only causes misunderstanding but also obscures the true value of serious scientific discoveries. Distinguishing between science and speculation does not mean stifling imagination. On the contrary, science encourages curiosity, but demands evidence, verifiability, and humility toward the unknown. 9. Missions to explore Mars. To unravel the history and habitability of Mars, humanity has launched a series of increasingly complex missions. Among them, autonomous robots play the role of extraterrestrial geologists. Curiosity, which landed in 2012, proved that Mars once had a habitable environment. It detected minerals that formed in water, organic molecules, and the transformation of methane over time. Perseverance, which landed in 2021, carried an even bolder goal: to search for ancient biosignatures and collect rock samples to bring back to Earth. This rover operates within the Jezero Basin, an ancient delta, potentially the best place to preserve traces of life. InSight doesn't move much, but it listens to Mars. It measures seismic tremors, helping scientists better understand the planet's internal structure and shed light on its thermal and magnetic history. Bringing Martian samples back to Earth is considered a major breakthrough. Laboratory analysis on Earth allows for the use of far more sophisticated equipment than what can be brought to Mars. This could be key to definitively determining whether Mars ever harbored life. X. The significance of Mars research. Studying Mars isn't just about answering the question of whether we're alone in the universe. More importantly, it helps us understand the nature of habitable planets, as well as the fragile conditions that sustain life over the long term. Mars is a prime example of planetary evolution. It demonstrates that the formation of water, an atmosphere, and even habitable environments does not guarantee the permanent existence of life. These elements need to remain stable for billions of years, an extremely demanding requirement. Through Mars, science has gained a better understanding of the central role of the planet's magnetic field. Without a magnetic field, the atmosphere would be easily eroded. Water would disappear, and the climate would become harsh. Earth still has a strong magnetic field, but it is not immutable. Understanding how Mars lost its magnetic field helps us better appreciate the value of the invisible shield protecting life on our planet. Studying Mars also contributes to answering a major cosmological question: is life common or rare? If Mars once had life, even if only microorganisms, it suggests that life can form relatively easily when conditions are right. Conversely, if Mars never had life, even if it did have water and energy, then life may be a much rarer phenomenon than we think. Furthermore, Mars serves as a lesson in planetary climate change. While the causes on Mars were natural, not due to intelligent life, the end result, loss of atmosphere, global cooling, and aridity, is a powerful reminder. A planet can be completely transformed if its regulatory mechanisms are disrupted. From this perspective, Mars research is not just space science, but also survival science. It helps humanity see the potential future of Earth in extreme scenarios, thereby better understanding the responsibility to protect the systems that currently sustain life. Ultimately, Mars serves as a giant natural laboratory where hypotheses about planetary geology, climate, biology, and physics can be tested. Every rock sample, every measurement, every image sent back adds a piece to the overall picture of how worlds are born, develop, and decay. 11. Conclusion: Mars is clear evidence that a planet can completely change its own destiny. From a world that once had water, a thick atmosphere, and the potential for life, it has become a cold, dry, and almost lifeless planet. Mars' journey is not a story of instantaneous catastrophe, but rather a slow, gradual decline spanning billions of years. There is no single moment of tragedy, only small, cumulative changes over time, from a cooling core, weakening magnetic field, thinning atmosphere, and the disappearance of water. It is this slow pace that makes the story of Mars so thought-provoking. It shows that life doesn't disappear in a single shock, but can be gradually eroded by seemingly insignificant changes. This is a profound lesson for how we view the future of Earth. Exploring Mars isn't just about satisfying a curiosity about extraterrestrial life. It's a journey of self-reflection. What makes Earth different? Is it its size? Its magnetic field? Its position in the solar system? Or is it a fragile combination of all those factors? As robots silently move across the crimson surface of Mars, they are not merely surveying a distant planet. They are rereading the history of a world that has lost its chance to become a second Earth. And in that silence, Mars sends humanity a wordless message. Life is more precious, rare, and vulnerable than we imagine. Understanding Mars will not only help us search for life out there, but also help us cherish and protect life right here on the only blue planet we know. When you look at Mars today, you're not just looking at a dead planet. You're looking at a possibility that once existed and has been lost. Mars didn't collapse in an instantaneous catastrophe. It didn't explode. It wasn't destroyed by a collision. It just cooled down. Its magnetic field weakened. Its atmosphere thinned. Water disappeared. And life, if it ever existed, quietly retreated from the planet's surface. That story makes Mars a rare scientific example, showing how a planet can completely change its destiny simply by losing a few seemingly invisible elements. And that's why studying Mars isn't just about searching for extraterrestrial life. It's about humanity learning to protect Earth, learning to appreciate its magnetic field, atmosphere, water, and the delicate balance that sustains our lives every day. We may find traces of ancient life on Mars. We may not. But whatever the answer, the Red Planet has already fulfilled an important role, reminding humanity that nothing guarantees the survival of life forever. If you found this video gave you a new perspective on the universe, don't forget to leave a like, subscribe to the channel, and share your thoughts. Because understanding other planets is sometimes the best way to understand and protect the only planet we have.